Welcome to this lecture. This is in continuation to our earlier discussion on the plate fin heat exchanger, and today we will be trying to discuss about the fabrication techniques of the plate fin type heat exchangers. So, here we have talked about the cross flow type and the counter flow type heat exchanger, and these are two fluid stream heat exchangers. So, here in this case only fluid 1 and fluid 2 are seen. I mean, this is fluid 1, this is fluid 2 moving out, and this is fluid 2 which is coming in and coming out through this exchanger. This is the cross flow type, and we also discussed about the counter flow heat exchanger configuration, where we have seen that we need a distributor to distribute the flow. I mean, from when it is coming, this is the nozzle, then we have the header, then we have the distributor to allow the flow to come in and then getting distributed and coming like this. Finally, this moves out from this distributor fin and this distributor fin assembly, and finally it is getting collected to this header and the nozzle and moving out. So, when it is happening in this layer, we have this is the sidebar, and in the next layer we have some different fluid number 2, which is flowing in this direction, and they are forming a counter current pattern to each other. So, how do we fabricate this kind of heat exchangers? So, while fabricating this kind of exchangers, we need to concentrate on quite a few things, and one of them is the fin. We need separating plate, we need headers, we need the sidebars, we need the cap seats. Cap seats are the top cover and the bottom cover, and of course the header and the nozzles. So, and in case of counter current exchanger, we need this distributor fins, appropriate distributor fins on each side and each layer. So, how do we fabricate this kind of exchanges? We will briefly discuss about those techniques, and as you can understand that we have the primary heat transfer surface area, and with that one we have to connect the fins, and we need a good thermal contact, otherwise they are going to introduce some kind of resistances which will ultimately degrade the thermal performance of the heat exchanger. So, we need to ensure a good contact. At the same time, we need to also ensure that there is no leakage or puncture of the separating plate, so that the fluid 1 and fluid 2 or any other fluid, they are mixing with each other. So, that we also have to ensure. So, we have a very stringent requirement, particularly in terms of the aluminum brazed aluminum plate fin heat exchanger, as we have discussed earlier, because the solidus and the liquidus temperature of aluminum is very close, and we need a very stringent temperature requirement in the furnace or in the deep brazing. I mean, we will discuss about that in the later slides. So, if you now look into this construction wise, the cross flow, as you have understood, I mean, this is a very simple arrangement where one layer will we have a separating seat, or the last one will be termed as the cap seat. So, this cap sheet will be there on the bottom and on the top, and we have one cap seat. On top of it we have this sidebar. On both the sides we have the sidebars. It is placed on top of that cap seat. Then we have the fin. This fin as this is a complete fin which is placed on top of this cap seat. Then we have another layer of this plate, and then we have this sidebar arranged on this side, and this is another fin. It may be of similar type or it may be of different type. Then we have another plate, and on top of it again we have this kind of fin arrangement like this. So, depending on the flow rate and the calculation of the number of layers, we have to put those many number of layers one on top of the other, and this whole assembly has to be put inside a fixer, so that they can be held permanently or rigidly within within a small volume or in a volume, and then the whole assembly has to be placed either in a furnace or in a molten bath. So, this is how it is done in a cross flow exchanger. This is the layer arrangement, and this is relatively simpler because we have only 4 directions to designated, say for fluid 1, this is the fluid 1 in and fluid 1 out. Similarly, we have another 2 layers, I mean 2 sides, this is another side from which one fluid can come out and this moves out, this will come in and this is how it moves out. So, we have 4 sides, necessary 4 sides for the flow in and out for the 2 fluids. So, this is possible in a cross flow exchanger, but in case of a counter current exchanger, that this geometry is bit different. So, what we do in counter current exchanger, we first put say this is imagine this is the cap sheet of one end, and this is blue in color. So, that it's you need to remember this blue one is a cap sheet for the bottom one, and then we put another layer of say what is called for fluid 1, which is you have designed it with a blue color 1, and this blue color 1 fluid is just on top of the cap sheet. We have placed, this is the sidebar, we have arranged it like this, and another sidebar is like this, this is another sidebar, and we have the distributor fin. One distributor fin is from here to here, then we have another distributor fin, we have arranged it like this, then we have the main fin in this region, then we have another distributor fin like this, and this is the other distributor fin. So, as a result, we find 1, 2, 3, 4, 5 different sections of the fins cut into appropriate dimension, and this distributor fin, as you can understand, that this flow will be coming over here, and this may not reach to this for this part. So, what we need to do, we need to select a type of fin such that this fluid will come in and will be coming out of this region to this region. So, we need to put some kind of perforated fin, so that this fluid will be flowing up to this last end of this one. And if you look carefully into this part, that you will find that this length, if it is like this, this is where it is having the least length, and here it will find the longest path to move out. Now, what happens to this? There you will find this is having the smallest length, but here you have the least length. So, as a result, here you have some kind of length, this is quite longer, and here this fluid has to travel all the way over here, and then here it finds small path. So, this path is longer on this side. For this fluid which is flowing from this end to this end, this path is longer. As a result, you will find the total length traveled by the fluid from this end to this end, whether or from this path to this path, is almost equal, so that there is least amount of maldistribution of the fluid. Otherwise, the people will have the tendency to follow the least path, and it will try, if it finds more resistance to this path, it will try to avoid that corner, and obviously we will not have the enough heat transfer occurring in these regions. So, we need to take into account of that one. So, this is the first layer where we find that the fluid, say this blue fluid, we call it fluid 1, and this fluid 1 is entering from this end to this, and it is moving out from this to this end. We define it as fluid number 1, and just on top of it, what we need to put is another separating plate. So, if we now put another separating plate on top of it, now this separating plate, this whole part, I mean the cap sheet, then we have the fin assembly, then we have put another layer of plate. So, this plate is, this whole part is a particular layer for this fluid 1, and on top of it, now what we do is that we want to put for the second fluid. Now, second fluid is coming from this end, this is fluid 2, this is fluid 2, and this fluid 2 is entering from right side to, and it is moving out from this end. So, now here also, as you can see, we have a distributor on this side, then we have distributor on this end, and this is the main fin. This main fin, it is a kind of wavy fin, or you can say it is a herringbone type of fin. Then we again have a distributor on this side and distributor on this side to take it out of this one. So, now what we have is basically one layer of the cap sheet, then one layer of fluid 1 layer, then we have separating plate, then we put another layer for the second fluid 2, and then as usual you can understand that we have to put separating plate. So, we will have this separating plate. So, this is constituting now one complete layer of fluid 1 and fluid 2 with the cap sheet at the bottom, and we have a separating plate on top of it. Now, if we wish, we can terminate on this one, and we have to just put on top of it another, this cap sheet. If we put on top of it, this will constitute a heat exchanger with a single layer of fluid A and fluid 1 and fluid 2. But often we will find that a single layer of such flow or fluid flow is not good enough. So, we need to put multiple layers of these two fluids. So, first of all, that was the fluid number 1, then on top of it we have fluid number 2, and this is like that we were going to arrange them. So, on top of it again we need fluid 1 and fluid 2, and like that it will continue. So, we have to according to the thermohydraulic design of this heat exchangers, we need such a number of layers and such kind of layers with the appropriate headers, the side bars and all. If we go back to this earlier slide, earlier one, previous one, you will find that here the sidebars are arranged in such a way that it is on this side. This is here, this side is like this, and we have this sidebar on this side, so that the fluid 2 is guided like this and it is coming like this. So, now if we look into the other layers, so as we have said that there would be multiple layers. So, we may need another fluid 1, and on top of it we will put another separating plate, on top of it again we put another fluid. So, then probably we have to put I mean, if it is all the required number of, when the required number of layers are put, then we put again the cap sheet, and that cap sheet will terminate or complete the assembly, and the whole assembly will look like this, and finally we will have this kind of counter current exchanger arrangement. So, this is what is the counter current exchanger. But this exchanger we do not get really in this form from the beginning. So, as I was telling in the earlier slide, that we first of all make the layers, requisite number of layers, then we take help of the brazing processes, where there are different type of brazing. Usually it is the deep brazing, and another part is the vacuum brazing. So, these are the two typical type of brazing we take help of to fabricate this kind of brazed aluminum plate fin type of heat exchangers. So, we will try to look into these processes quickly. First of all, if we look into the deep brazing process, we will find that first of all we make an assembly of this separating plate, then fin, then distributors, and this that is all, and with the cap sheets. All these things are first cleaned, and then these clean parts are assembled together, and when it is assembled, with the separating plate, what we do is that we put the appropriate filler material. So, here we have the appropriate filler material. We will find that this is necessary when we do brazing. If you are aware of, you will find that we need flux, we need the filler material, then we need the heating. So, that the filler material will melt in presence of the appropriate flux, and then that will join the parent material with the auxiliary part that we are going to attach to this separating plate. Now, here this first of all, as we have said, that clean parts are assembled together, and they are jigged, jigging parts with the filler material, jigging part with the filler material. All these separating plates and filler materials are the parts will have the filler material associated with that one, and that complete assembly is then preheated. As you have noticed that assembly that we have talked about, say imagine that the separating plates are filled with a layer of say filler material, and on top of it we have put the fin, and that whole assembly is within a fixture. It is within a we have a fixture to hold that one tightly in position, and that whole assembly has been preheated. So, once we have preheated it, we put it in a salt and flux bath, and that is kept nearly about 540 degrees centigrade. But why do we need a preheating? We will come to that part. So, like this one, as we were saying, that the aluminum plate, if this is the aluminum plate, we will find that the plate on top of it is filled with, or we have a filler material cladded on top of the aluminum material. This yellow color one is the filler material. It is integrated with that one, and this filler material, this fin, this is just only one fin that is shown on top of it. There will be another filler material filled separating plate. So, like that, this whole assembly which has been preheated, and then we have put it in the molten flux electrolyte electrode. So, this whole assembly I mean it has been preheated and this temperature is nearly 540 degrees centigrade or 538 degrees centigrade. So, why preheating is necessary? Otherwise, that will unnecessarily cool down depending on the size of this heat exchanger. It will unnecessarily cool down this molten bath. Okay. So, if it is preheated just few degrees below the 540 degree centigrade temperature, so it will not necessarily change the molten bath temperature and it will quickly achieve the temperature of the molten bath, and in presence of this molten flux, this filler material will now melt and they will bond this fin with the parent material aluminum. This is also made of aluminum and this is also, I mean mostly this is 3000 series, we have already talked about it. So, this is immersed in that molten flux and this flux will help to I mean make a bond between the filler and the parent material. So, that is how we will be getting joint between. So, finally, when it is taken out of this molten bath, we will find that we have a kind of joint between, I mean a joint will be formed between the plate and the fin. So, automatically this will be I mean this is where is the joint between the aluminum plate and the fin. So, this will ensure that there is a good thermal contact between this plate and the fin, which is necessary, otherwise we will have a kind of thermal contact resistance between the fin and the plate. So, to ensure that we have a good thermal contact and to have a good mechanical assembly or I mean construction. So, we put I mean we allow it to go through this brazing process. Okay. So, now if we look at it will be taken out of this bath and it will remain at quite high temperature. So, 540 degrees centigrade temperature. So, we need to quench it and cool it, and then what we need to do is that we need to remove the additional flux and we have to wash it appropriately before we take the whole I mean the whole assembly for the next kind of operation or the inspection, whether we have got a good joint or not. So, we will talk about that inspection part later on. So, this is in a nutshell about the dip brazing technique. We have quite a good I mean quite some advantages with this molten flux electrolyte, but one of them is that there is less chance of I mean distortion, which often we find in it may occur due to a different kind of what is called preheating during the other brazing techniques. But this molten flux material cost becomes maybe substantial. I mean or depending on the size of the heat exchanger, we often go for a brazed aluminum or I mean brazing by dip brazing or by vacuum brazing. So, the next one is about the vacuum brazing. So, here the pre-cleaning of the parts is again necessary and we need to take appropriate action so that there is no grease and all on these plate fin surfaces. Afterwards, we need to again assemble them, as we have said, appropriate I mean for the cross flow or counter current configuration. Then we put I mean here this is in contrast to the I mean dip brazing technique. Here we put the filler, both the filler and flux on top of it. It is cladded basically on the aluminum. This is cladded on top of the aluminum plate, and then this whole assembly I mean one this is just a single layer we have shown, where we have the fin and this is the plate cladded with filler and the flux, and this whole unit is within a fixer. I mean this is within a fixer, and this fixer will be placed inside what is called the vacuum brazing furnace. And why we need a vacuum? Because we know that in presence of the oxygen, if we try to raise the temperature to a high degree, we will find that the aluminum plates may be getting oxidized easily. So, and that will be very difficult to break that oxide layers and to make a good joint between the plate and the fin. To ensure that there is no oxygen, we create a vacuum, or sometimes we put an inert gas in the system, so that there is no oxygen to create aluminum oxide layers. So, now we place it inside the vacuum, and gradually we raise the temperature of this whole assembly. Depending on the size of the assembly, we slowly heat it up, and sometime we give some kind of heating, and followed by soaking time, so that the whole assembly is getting heated up to a prerequisite time. And when it is reaching to that desired temperature, as we have said, nearly about 540 degrees centigrade and around. So, we give a ramp and then soaking time in the vacuum brazing furnace, so as to reach the desired temperature. And when it reaches that temperature, we allow it to be there for some time, and then again we need to cool it down. Sometime we cool it down or allow it to naturally cool down, or otherwise we often do it we quench it, and then we go for the cooling or quenching, and then so finally we will have a brazing of this kind of brazing between the plate and the fin, and then we go for the inspection. So, this inspection is basically we need to ensure whether there is any kind of leakage or not. So, we will discuss about that part sometime later. So, when we get finally, this is the kind of heat exchanger code we will get, we call it heat exchanger code. So, we have only the sidebars and the fins and the plates. So, it is not just because it is not like a heat exchanger. This is only a heat exchanger only when we put the headers on 4 sides, or different sides, it becomes it behaves like a heat exchanger. So, this is when we have this heat exchanger core fitted with the sidebars and the headers, we will get a appropriate heat exchanger. Depending on the construction, it may be a cross flow exchanger, it may be a counter current exchanger. Thank you for your attention.